you receive anything from schools you applied to?
No.
No replies?
No. I already have.
Oh, thank you. So,
После здесь тоже будет стирать, мне кажется, очень новый документ создать.
окей.
А вот
Она слева, на левой доске появляется.
А здесь?
а что здесь?
А, не работает?
Может, просто перетянуть на
А как
интерфейс?
здесь писать?
Является.
Чё? А, здорово. Просто
Внизу страницы слева.
Нет.
Нет. Создать новый документ проще будет, просто файл создать. Он тут не реагирует, конечно, да.
О, красиво. Okay. Last time we recalled something about the symmetric functions in lambda, and also about the Frobenius ring. R. And now this Grothendieck ring exists in two incarnations. So on the one hand, it is the Grothendieck group of representations of a symmetric group. On the other hand, just via characters, it is the ring of invariant functions, central functions of the symmetric group. Okay. And now Frobenius constructed the characteristic map. So at the level of functions, it takes function f. Now f is the function on the conjugacy classes. The conjugacy classes are numbered by partitions. So f is essentially functions of partitions, right? maybe we don't yet really know that it is two integers. I mean, the characters of a symmetric group could be algebraic integers. Yeah, not necessarily. Well, like in the case of characters of GL2, you could notice that the values were not just God-given integers. Yeah, they were algebraic integers. But well, I can write here Q, for example. A posteriori, everything will be just z-valued. But if you wish, well, maybe I could even start with complex numbers. Anyway, we said f of lambda well goes to the well maybe sorry well once again f. So f is a function of partitions, and maybe f has degree n, like here. So f goes to the sum over all partitions of n, z lambda inverse f of lambda p lambda. So p lambda is the power function, and this is z lambda was introduced. It was the order of centralizer of this type element in the symmetric group. So it's the same as 1 over n factorial, so the order of symmetric group, the sum over all elements, so W in symmetric group, f of W, and then just the class of this element. How's it? Cycle class, I forgot.
Cycle type.
Cycle type. Cycle type is some partition, and you take the corresponding power function. Okay. Now, the useful facts is that first of all, the characteristic map is a homomorphism. Well, you just check it explicitly, straightforwardly. Also, it is an isometry. So we introduced the scalar product on lambda last time. And also there's always scalar product on the class functions, or say on the Grothendieck group, that class of V1, class of V2 is dimension of form Sn from V1 to V2. And you can also write it down in terms of functions, class functions of the group. Does everybody remember how to write this scalar product in terms of class functions on the group? Or does nobody remember? Okay. Maybe I shall write it down. Given two functions, f1, f2, on the symmetric group, we divide by the order of the group, and then the sum over all elements, say W, in the group, f1 of W, f2. See, I can either write complex conjugation, but then it will look somewhat Hermitian, or I can write W inverse. So, yeah. and it's the same for reasons that I hope are clear. Yeah. Yeah. Okay. What else? Oops. No. Okay. So tensor by the one-dimensional sign representation goes to the involution omega on lambda. Okay, hopefully that's it. And now, what do we know? Well, maybe I can continue with the facts. Certainly, the trivial character of the identity representation, like see, trivial representation, well, the class of this, maybe I should call it 1 with subscript n. Okay, just by this formula, it goes to Hn, the complete symmetric function, and hence, if we induce from S lambda to Sn. I mean, we have a partition. For example, if we have a partition in 2 parts, then we have a symmetric group, the product of those 2. And this was used to define the multiplication, right? And well, S lambda is the product of S lambda 1 times S lambda 2 times so on. So it's a subgroup of Sn. So if we induce trivial representation, then this goes to H lambda just by definition. Sorry. Oh, sorry. Well, it's lambda. Okay, and now it's well, easy to prove. The classes of such representations for integral basis of Rn. I mean, say by the Young construction with symmetrizers, you can see that such thing contains the irreducible representation corresponding to lambda with multiplicity 1 and some junk with smaller partitions. Okay, so the transition matrix is strictly upper triangular, so it is the basis of Rn, and hence we, since H lambda also form a basis, we see that this character map is an isomorphism of rings. Okay, and now the last step is that Schur functions S lambda, by the way, they're called Schur functions because Isaiah Schur studied them, but they were introduced by Jacobi maybe 100 years before Schur was born, something like this. they form an orthonormal basis of lambda. Well, it's a fact you can check, or you're supposed to know. Huh?
It's the definition
Of what?
the
Scalar product? Well, it's one of the, yes, one of equivalent definitions of scalar product, right? So they form an orthonormal basis. Hence, the elements in their preimage in the Frobenius ring also form an orthonormal basis, and they must be plus minus characters, because we know that the characters also do form an orthonormal basis. And any two orthonormal bases in a Z module, they differ by permutation and the change of signs. Okay? So necessarily, well, maybe I'll continue here, but I don't know. Okay, so they're irreducible characters. And then you check, well, you compute the value at 1 and you see that it's positive, so it must be just this. Okay? And this is essentially the argument of Frobenius. And somehow, for Frobenius, it was not so outrageous because he even didn't define first the characters as traits of representations. For him, characters were functions with a certain functional equations. And he wanted to find them, and he found them in this way.
But why is
Yes.
lambda on the left and on the right is the same?
It's just
Difference.
it's just a notation, if you wish. Well, it should be compatible with this upper triangular matrix, and it is. So everything will be fine. But from the modern point of view, this approach is somewhat arrogant, because you don't really construct any representations, don't compute anything. You will somehow start with God-given Jacobi-Schur functions and prove that they are characters. And it is not very satisfactory from the modern point of view, but that's the historical approach. And the approach we'll take to the characters of GLN over FQ will be exactly the same, just literally the same. Okay, so I do something like this, yeah? I'm afraid I will not succeed. Yeah, I see.
Try with
What
one
we
finger.
with one finger, okay.
No?
No, it's gonna worse. Maybe she did not have my finger. Oh, great. Oh, okay. Uh-huh. And now I press here? Or
Yeah.
Okay. Okay. So now I must explain. First of all, in what sense did we compute the characters? So the character table is just table of numbers, and the value of character is some conjugacy class. Yes. Why does this Frobenius theorem that does compute the characters? Well, so the corollary is that the value of character chi lambda at the conjugacy class mu is the pairing of S lambda and P mu. Okay, so it's algorithmically computable. in this form, so this character table is the transition matrix from between Schur and power functions. So maybe let me write down all the transition matrices. First of all, to write down matrices, we need some order on partitions. And this order will be lexicographical order. So first of all, there is the dominance order. And then we say that lambda is bigger than mu if lambda 1 is at least mu 1, lambda 1 plus lambda 2 is at least mu 1 plus mu 2, and so on, but in the end we have an equality. Okay, and there's also lexicographical order. We write lambda is lexicographically bigger than mu, if you know what. So for example, if you start with n, it's bigger than lexicographically than anything, and then anything is bigger than 1 to the power n. Okay, and well, if lambda is bigger than mu, then lambda is bigger than mu lexicographically. But this order is not total, or what's it called? Is it total order? Yeah. This is not a linear order.
So if lambda,
not linear.
the size of lambda and mu are different, they are not.
So no, the sizes are always the same. Otherwise, they're comparable. You never need to compare different sizes. All the transition matrices are between partitions of the same size. This we won't care about at all. But it's not linear for n. I think at least 5. But lexicographical order is certainly linear, and it's some refinement of the dominance order. Okay. So somewhat in reality, everything will be governed by the dominance order. But in order to write down matrices, we need some total order, like linear order, and this is the lexicographical order. Okay, so we will speak of upper triangular matrices or strictly upper triangular matrices with respect to this lexicographical order. So we say that a matrix m lambda mu is strictly upper triangular. If m lambda mu is 0 unless lambda is bigger or equal to mu, and lambda is 1. Okay, if this is so, then this matrix is invertible. Now what do I do here? Just up? What is up?
Yeah.
No? No.
At the top there is a razor. Right. No, to the right. Look at.
To the right.
At the center.
Sorry. Here, right.
Не знаю, может быть.
Okay.
Наверное, просто.
Есть ощущение
Ага, very good, thank you. And now?
Ну, просто хотелось бы кнопку, чтобы
No.
А нет?
сразу все
Может быть,
очистить.
это нужно убрать.
Очистить, там вот сюда очистить.
Двумя.
Yeah. Thank you. Oh. Ага. Great, thank you. Ага. Now, so given two bases like u lambda and v lambda, we get the transition matrix M of u v such that u lambda is sum over mu m lambda mu v mu. Okay. Then, for example, m u v times m v w is equal to m u w. Okay. Now, if u prime and v prime, sorry, are the dual bases to those. Then the transition matrix M U prime V prime equals M over V U transposed, or else M of U V adjoint, meaning M of U V transposed inverse or inverse transposed. Okay. Now what else? M of omega U omega V is the same as M of U V, and finally we'll need the matrix J lambda mu is 1 if lambda transposed equals mu and 0 otherwise. And maybe recall from the last time that the transition matrix between the Schur and monomial functions is formed by Kostka numbers. Okay. Now, let's say, now. Oh, it works. So let me draw this transition table. We will have the elementary functions, the complete symmetric functions, monomial and Schur. And the same here. And so certainly on the diagonal L always 1, and here K transposed J, K adjoint, K transposed J, K, K transposed J, here K transposed J, K adjoint, 1, K transposed K, K transposed, K inverse J, K adjoint, K inverse K adjoint, 1, K inverse, J, K adjoint, K adjoint, K 1. Okay, so these are transition matrices. Okay. And now, well, that's essentially all the recollections I wanted to make about symmetric functions. So now let's move on to GLNs. As I said, the strategy will be the same as a Fabinho strategy for symmetric groups. So we will need to organize the direct sum over all n, k groups of GLN FQ. Oops. So what shall I do?
Да. Просто пальцем перетяните его на левую доску.
This. Ой.
Снова.
Продолжайте.
Ну, просто снова перетяните.
Сверху.
This.
Да.
Окей.
Еще справа сверху на квадратик. Вот.
На левой доске справа наверху квадратик.
На самом верху.
Совсем наверху, чтобы окно открыть было.
Самый-самый вверх вправо на левой доске.
Вверх, вправо.
Вот рядом с крестиком.
Не вверх,
Да, выше, 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 еще выше. Еще выше.
Выше?
Ага.
Like this? Okay, so maybe let's call this GN. So I want some ring structure on this. Okay, and probably you may guess what will be the string structure.
The same induced representation.
Yes, absolutely. Well, maybe let me call it R script. Sorry. No. Yes. we'll use the induction, but it will be a parabolic induction. So with respect to the parabolic induction. Namely, given, say, Gn and Gk, we certainly have an embedding of Gn times Gk into Gk plus n, but there is something in between. So this is k, this is n, and we have this product of groups, but we also want to have this. Okay, so it's embedded into some parabolic subgroup P and K, which is embedded here. And in fact, well, there is such an embedding, as you see, but what is much more important is such a projection. Okay, namely, this is a normal, this is unipotent subgroup, normal subgroup, and you may take quotient by this and project onto that such product. So the parabolic induction given two representations like V n and dk in gk. We take the induction of V n tensor V k, but not from the product Gn and Gk, but from the parabolic subgroup onto G n plus k. Okay, so you take as a product, it's a representation of Gn times Gk. Now you compose with this projection, you obtain a representation of this parabolic subgroup, and then you induce from it to Gn and plus k.
What is P and K again?
What is what?
P and
P and K.
Yeah.
This subgroup, so it, well, it is, you take f, for example, q to the power k inside f q to the power n plus k, okay, and then this p and k is the set of g in gk plus n, such that they preserve this subspace. Certainly you can do it in the opposite order. You can use the subspace of dimension n. Okay, but they will be conjugate, so it doesn't really matter. The induced representations will be isomorphic. But it's important for the commutativity of induction, but it really doesn't matter. Okay, so So for example, when we considered the induced representations of GL2, it was an example of such a construction. Yeah, we started from GL1 and GL1, took two characters and induced them in this way.
So the upper right coordinate doesn't X.
Yes, it acts trivially, yes. Uh, well, okay, and well, more generally, I can induce from a Borel subgroup of GLN, for example. Borel means upper triangular, but then on the diagonal I will have characters mu1 and so on, and mu_n. So this will be the product of mu1, mu2, and mu_n in this sense. Okay. And then it was, I think, January 31st, home assignment, and you had to compute the endomorphism algebra of this, maybe not of this, when they were all equal to 1. Yeah, the endomorphism algebra of the induced representation from Borel to GL n of well, I can say 1, 1, 1, or I can twist by mu. It doesn't really matter. It will just twist by a central character. And this was the finite Ivahori-Haker algebra. Okay, and now the fact. Well, maybe first let me give a terminology definition that an irreducible representation V over Gn is called cuspidal if it is orthogonal to anything induced. But in this sense, from P, say K, P, K, L, well, to G, N, of anything at all, W is equal to 0 for any K, L, and W. But certainly it must be some proper subgroup, so K is not 0 and A is not, L is not 0. Okay, so it is the same terminology we used for GL2. There were induced representations, Steinberg characters, and also cuspidal that were separated from those. And Vladislav, maybe you can do this.
New page.
New page. And where is new page?
I think it's
The
шестая кнопка.
green one. In the
Нет,
middle.
в первом ряду шестая кнопка.
Here.
The middle.
Да, вот
The
шестая.
middle of the screen.
Huh?
This line, the middle of the screen.
Это такой зеленый
Шестая.
крестик.
Раз, два, три, четыре, пять, шесть. Вот шестая.
Oh, the green.
Да нет, мне кажется, зеленый крестик, который правее. Там прям страничка нарисована, зеленый крестик.
Oh, great. And now?
Zoom.
No. So what can I do?
Вы двумя пальцами
А
делайте, это не больше, чем два, чтобы прикосновение было. Он не умеет, скорее всего, больше распознавать.
Okay, so the fact of life is the following. So, suppose that, well, either, how to say this? So V, K and VL are distinct cuspidal representations of GK and GL. Well, if K is not equal to L, then certainly they are distinct. If K is equal to L, they may coincide, but I require them to be distinct. Then this induced from parabolic KL to GK plus L of VK times VL is reducible. And B, if I take, I will iterate this construction. So I have a parabolic which looks like this. P, K, and so on, n times. And I induce some Vk which is cuspidal. And then I take its endomorphisms. Then this is the same Ivahori-Hecke algebra. Well, certainly any representation of one-dimensional torus is cuspidal because it can be induced from anything smaller. Okay, so this is a particular case, but it turns out that there is nothing else.
I'm sorry, VK
Yes.
is any or any cuspidal?
Irreducible cuspidal. Okay, so you get, this is some very basic Ivahori-Hecke algebra, and you get nothing else. Whatever induced representations you consider, all the endomorphism algebras are just Ivahori-Hecke algebras. So sometimes they are irreducible, there are no endomorphisms at all, just complex numbers. If not, they are just Ivahori-Hecke algebras. Okay, so in a sense, if we could somehow find the character table of cuspidal representations, like what we did for GL2 last time, then, well, knowing enough about Ivahori-Hecke algebras, we could find all the irreducible characters. But, well, this would be a more honest approach, but this is not the road we'll take. We'll take this Frobenius approach. Okay, so let's
May I have
yes.
a question?
Yes.
If in this condition, instead of any W, we
Yes.
write VK tensor VL, will the condition be equivalent or not?
Oh, certainly, yes. Yes.
Yes.
Because everything, well, just by inductions. This W, either it's induced from from some smaller GGL, or it is capital, and then it is just the product of two. So it doesn't matter. Here you can assume that this W is just the product of caspitals. It's enough. Okay. So, well, so let us describe the multiplication. This multiplication R script in terms of functions. Central functions. So, first of all, what are central functions? And I understand that there are functions on GLN of Q, but invariant with respect to conjugation. But maybe it can be yes. No. Oh, yes. So there is some more geometric way to think about such functions, not just by definition. So first of all, what is GLN of Q? It is formed by invertible n by n matrices. Invertible n by n matrices are well, they are representations of the Laurent polynomial ring, right? So G in GL and FQ. By the way, it started, well, now it reacts much faster to my writing. I don't know why, but I'm just happy. Representation. Maybe n-dimensional over FQ over T invertible, yeah? The Laurent polynomial ring. Namely, T goes to okay, and what are the class functions? In these terms, what are they? So the elements are just representations. And what are the class functions? So when two elements are conjugate? Right. Right, absolutely. So these are just functions on the isomorphism classes over n-dimensional representations. Fine. And now I claim that this multiplication, so I defined it at the level of representations. Then to representations I can associate characters, they will be class functions, and I want to rewrite this parabolic induction operation in terms of the class functions. Yeah, that's what I am doing now. Is the following operation. Well, it is called Philip Hall multiplication. So I start with just I'm out of notational letters. I want to call it R, but sorry, maybe let me call it such R. Okay, so such R will be the set of isomorphism classes R. Okay, the set of isomorphism classes over representations. Sorry, it's K. Okay. So we have R K. We have R L. And we want to produce, well, I have a function, maybe Fk with tensor with some function Fl. And we want to produce a function on R K plus L. So how do we do this? Well, I consider some intermediate space that will be called R K L. Oops. Okay, so R K L will be the space of isomorphism classes of representations. K plus L. But also a subspace plus a subspace V of dimension K. Such that rho of T respects this subspace.
I don't get it.
Yes.
K is fixed for all RKL or is for any elements of the set it's different?
Who is fixed? VK?
K, yes. Is it the same for all elements of RKL?
Just RKL is the sort of isomorphism classes of pairs, rho and VK. Okay. Fine. But now, unfortunately, the idea is given two functions like this, somehow lift them here, and then just integrate to RK plus L, just over all the choices of VK. So some over all the possible choices of VK. But you cannot quite do this. So instead, you need RKL tilde. And this is the set of maybe quadruples R, V, K, and also an isomorphism V, K is, well, fix an isomorphism. So fix a basis F, Q, K, and we also fix an isomorphism as a basis in the quotient space V, K plus L, or if you wish, the ambient space F, Q, K plus L modulo VK. We identify, so we choose a basis with F, Q, L. Okay, so what we do have is this, and now we can forget those identifications and project onto RK plus L, RKL. So we forget. Maybe let me call this identification K. Identification L. So forget I, K, and I, L. And here we forget VK. Okay. Now the nice thing about this tilde is that it projects onto RK times RL, right? Because we just so it projects to RK times RL. Namely, we just take well, I don't know how to say. Maybe I K rho I K inverse. Maybe a rho restricted to VK, and IL rho restricted to F Q K plus L modular VK IL inverse. after we identify this abstract k-dimensional subspace and its abstract l-dimensional quotient with the concrete fk and fl, we can obtain a representation in fkl or f in fk or fl, right? So we do have such a diagram. And now, given two functions, well, maybe let me call this p, q, and n. Maybe here I can say that I don't know, maybe here. So there exists a unique fkl on rkl, such that when you pull back fk tensor fl, then it is the pullback of fkl. So the assumption that our functions were class functions, they only depended on the isomorphism class of representations, results in the fact that when we lift them to this big space, it necessarily descends to this RKL space, sort of Grassmannian. Okay? And then finally, Fk whole multiplication with FL is defined as the push forward of FKL. So I mean, you take the sum over all the fibers of this map. Okay, this is the description of our operation of parabolic induction at the level of functions. Okay, and now let me make the following remark, but I have to erase this, unfortunately, yeah? Or that, maybe you have some preference. No preference.
Maybe erase the right board but leaves the last.
This diagram?
Yes.
Okay. Like this. No. No. This. So the first remark is that we never really used the invertibility of T. So, well, for the same price, we get the Philip Hall multiplication on the functions on all the matrices, not necessarily invertible matrices. But invariant with respect to the same conjugation. So here we conjugate with the same group GLN, but the functions are not necessarily invertible matrices.
So in this claim, it isn't used.
Never, we never used this.
We never proved claim.
We didn't prove claim, but it's maybe up to you. So you have to somehow just rewrite the definition of induction at level of functions, of class functions. Yeah, you know how it acts on representations. Now how it acts on characters. We also discussed this, so you know how it acts on functions, and then you will get just this. In more geometric terms, you get just this. And the second observation is that in GLN of FQ, there is the so-called nilpotent cone. Well, formed by nilpotent matrices. Okay, and then this multiplication preserves the functions supported on nilpotent cone. Just by its very definition, because if you know that you have a filtration and your operator was nilpotent both on subspace and on the quotient space, then it necessarily must be nilpotent on the whole space. The subalgebra. Sorry. So I don't know how to erase, but okay.
There is a razor on the top.
There is a razor on
At the middle of the screen. Yes.
Right.
Yes, yes, yes.
Thank you. Thank you. So functions. With nilpotent support. Or we could also work with functions on the invertible matrices and take unipotent support. Again, if your operator is unipotent on subspace and on the quotient space, it is unipotent altogether. And then there is an isomorphism between nilpotent cone and unipotent cone just by exponentiation. No, it's bad because we're in finite characteristic. Just 1 plus. 1 plus nilpotent matrix is a unipotent matrix. Okay. So, what we'll do for the next maybe month or so, at least a couple of weeks, we will compute this this algebra, and then it will turn out that everything else is trivially reduced to this algebra. So it contains all the important information, just not nilpotent things, and it's called the classical Philip Hall algebra. So it was introduced also about 100 years ago, maybe 80 years ago, but or no, maybe 70 years ago. But then, like 30 years ago, there was a certain renaissance of this theory, and we will study it maybe in May. Okay, so maybe let's say one more word. Oh, so we consider just an nilpotent cone is the or maybe again the quotient modulo GL of Q. This is the set of isomorphism classes. All representations. Now what over? So they will go to n-dimensional space, but so for invertible matrices we took Laurent polynomials. For not necessarily invertible matrices, just any polynomials. And if we want matrices to be nilpotent, then what?
The version.
Yeah. So we take FQ, formal power series, T, and then to just endomorphisms of Q. So since this is a formal variable, it necessarily must go to nilpotent. Otherwise, we'll have infinite series which diverges. Okay. So these are just isomorphism classes of FQ modules of length. So next time we will start studying the multiplication of such things. And also we could consider the arithmetic version, just periodic integers. And so, well, we know that this is just partitions, don't we? Right? Just by Jordan normal form, right? And those we also know that there are a number of partitions by the basic theorem of first year algebra, a classification of abelian groups. Okay, so we'll study simultaneously this and that. There will be no difference whatsoever. Okay, thank you.